Hello, calculus fans. We can do double integrals over more complicated regions, like this one. So here's a region described in polar coordinates, where we're saying that the values of theta are between alpha and beta, and then the r values lie between these two curves in polar coordinates. R equals h1 of theta and r equals h2 of theta. So that's an inner bounding curve and an outer bounding curve. In order to evaluate integrals over regions like this, we'll do something similar to what we did earlier, where we integrated over type 2 rectangular regions. We can combine the formulas from that section with those from this section, and we get this formula. If you have a function that's continuous on a polar region that looks like the set of all points r theta, where theta goes between alpha and beta, and r goes between h1 of theta and h2 of theta, then you can write the double integral of f over the region D as this iterated integral. It's the integral from alpha to beta, so that outside integral is with respect to theta, and then the inside integral goes from h1 of theta to h2 of theta, and then we transform the function by saying f of r cosine theta, r sine theta, and then once again, I remind you, don't forget the little r in there, the scale change factor. I mention that a lot because it's a common mistake to just forget about that r. So let's evaluate the double integral of x over the region D. Now D is going to be the first quadrant region that lies inside the circle x squared plus y squared equals 4, but outside the curve x squared plus y squared equals 2x. Now we know all about x squared plus y squared equals 4. It's a circle, centered at the origin, radius 2. Let's try to figure out what x squared plus y squared equals 2x looks like. Let's complete the square on this equation. So we move the 2x over to the left side, and then we have to add 1 to both sides. That's what would complete the square. And so we wind up with x minus 1 squared plus y squared equals 1. So actually, we do recognize this curve. It's a circle of radius 1, centered at 1, 0. So let's draw a picture of the entire region, keeping in mind that the original problem told us to just compute the integral over the first quadrant region. So here you can see the big circle, radius 2 centered at the origin. Here's a smaller circle, radius 1 centered at 1, 0. But we really just want the first quadrant region. So really the region we want is what's just in the first quadrant there. So it's kind of this funny looking shape that I'm outlining here like this. Just that. Let's try to describe this region in polar coordinates. Let's write down polar equations of each curve. The circle is very easily written in polar coordinates. That's just r equals 2. Now the other curve can be written in polar coordinates by replacing the x's and y's with r cosine theta and r sine theta, respectively. And of course, we also know that x squared plus y squared is equal to r squared. So, to transform this equation, we end up with r equals 2 cosine theta. We can describe this region in polar coordinates like this. It's the set of all points r theta, where theta goes between 0 and pi over 2. That's because we only want the first quadrant. And r goes between 2 cosine theta and 2. Let's now evaluate the integral. So the integral of x over the region D is going to be the integral from 0 to pi over 2, those are the bounds on theta, of the integral from 2 cosine theta to 2, those are the bounds on r, of r cosine theta comes from x. X turns into r cosine theta, and then we have r dr d theta. We just always have to have this r in here. Clean this up, combine the r's together, we get this. And if we integrate, we're just integrating with respect to r, we'll get 1/3 r squared cosine theta. And then that goes from 2 cosine theta to 2. So now we'll plug in those values of r. When we plug in those values of r, then we'll get this. So we have now the integral from 0 to pi over 2 of 8/3 cosine theta minus 8/3 cosine to the 4th theta. All right, I'll split this up. Now I'm just stalling for time. Now that first integral is really easy to evaluate. You just get 1. You work out the details. Let's focus on the second integral, which is a lot harder. Let's just show how to compute the integral from 0 to pi over 2 of cosine to the 4th theta d theta. The way we'll do this is make use of the half-angle formula cosine squared theta equals 1 plus cosine 2 theta over 2. We'll have to use that a couple of times. So we'll split the integrand up as cosine squared theta times cosine squared theta. We use the half-angle formula to transform this into 1 plus cosine 2 theta over 2 quantity squared. Multiply everything out. Notice there's a 1/4 that comes out in front. And now we need to use a half-angle formula again because we need to evaluate cosine squared 2 theta. So that turns into 1 plus cosine 4 theta over 2. Clean everything up, and this is what we get. And if we keep going, compute an antiderivative, then this is what we're going to end up with. That all works out to 3 pi over 16. Let's now take this result and go back to the original calculation and see what we get. So remember that we worked everything out to get to these two integrals, 8/3 times the integral from 0 to pi over 2 of cosine theta d theta minus 8/3 times the integral from 0 to pi over 2 of cosine to the 4th theta d theta. This first integral was very easy. This guy worked out to be 1, and then we just worked out what this integral is. So here's our final result. And everything boils down to 8/3 minus pi over 2. Okay, that's all for now.